One thing I've been noticing is that the AI world has taken a lot from the statistics community, but there's a pretty heavy divergence in what researchers in each field are paying the most attention to. Areas like statistical machine learning still exist, of course, but I think we all know what's sucking the air out of the room. So I wanted to speak with a statistician about his work and how he understands his work and his field. Ryan Tibshirani, my guest today, is a really interesting scholar because his work spans applications and theory at pretty different levels. You'll find common themes in his work, but also a variety of problems that he's worked on with different motivations. I find both his work and his reflection on it really thoughtful, and I hope you'll take something away from his articulation of what he does and how he does it. This is the Gradient Podcast. I'm Daniel Bashir. The best way you can help me out with this project is by sharing it with people you know and by leaving ratings and feedback. And now, without further ado, Ryan Tibshirani. Ryan, before we get into a couple of the papers that I have questions for you about, one thing that was actually, I guess, notable to me was when I first reached out to you about doing this interview, you were wondering whether I had intended that email for your dad. And so because of that, I'm kind of wondering about your path into statistics and how much, given his station in the statistics community, what that kind of looked like for you and whether that was maybe a path that was kind of always in mind or what that looked like for you.
It's a very fair question. It's a question I actually get not too infrequently either. I was always interested, at least as an undergraduate, let's say, and as a high schooler, I was interested in math and maybe early on physics as well. But in undergraduate, I actually studied math as my major. I took computer science as well. I didn't take any statistics as an undergraduate. And my introduction to statistics came through applied work that I was doing in summer internships. So I was working in a couple of different biology labs at Stanford as an undergraduate, and I had no training in statistics whatsoever, but I was doing some of the quantitative analysis that was associated with the experiments that were being run. So it's just stuff that I learned in order to be able to, be a good intern, basically. And the wonderful thing about my dad is that there was never any pressure, implicit or explicit, about me picking up stats. So it was something that I would talk to him about in order to kind of understand the grounding, but it was never something where I felt like I said there was pressure. And then I decided to pursue, I was deciding in between pursuing a math PhD and a statistics PhD. I applied to both sets of programs, and pursuing a statistics PhD, it was mostly done on a whim, to be honest. It wasn't like I said, I had a ton of experience about what that would look like. But from knowing people like my dad, and I knew a couple of his colleagues decently well as family friends, I understood that statistics was extraordinarily broad. So if I did a stats PhD and I wanted to do something very mathematical, then that was something that was in the cards that I could do. If I wanted to do something that was very applied, then that was also something that could be in the cards. And if I wanted to do something that was very computational or had more of a CS leaning, then that was also allowed in some sense. I think statistics is very unique in that way that what we consider home base or even adjacent to home base is very broad in a statistics PhD or a statistics program. And so I decided to go for it for that reason, just with the understanding that I hadn't really figured out what I wanted to do, and this was an opportunity that would kind of allow me to keep things pretty open. And I was obviously very glad I did it because I consider statistics my field now. I went to a PhD program in the same. So I attended my PhD in this. I did my PhD in the same department that my dad was a faculty. So that was an interesting experience because everybody knew my dad, both the people that I was taking classes from, like other professors, and my cohort, my students that I was taking classes with. They all knew my dad, and I'd say that was probably of all the time in my kind of career, that was probably the time that was most delicate in terms of the relationship, because as a student, you really have to prove yourself. You shouldn't be given anything as a student. I mean, you shouldn't be given anything at any point in your career, but especially as a student. We had qualifying exams at that point. So, there was a period where after the first year, we were taking exams that would permit us to continue onto the PhD. And had we not passed, that would be, game over for the PhD. And so that was a very delicate period. Like I had to be very careful that I didn't, well, that I was kind of trying to be completely independent, and also that I was not perceived as being, dependent on my dad in any way, because formally I was, having to be evaluated by the department in order to continue. After that, I'd say it was like after the first, year and a bit of my PhD, I'd say that it was extremely comfortable being in the same field as my dad. There was never any periods of being, worried about it or frustrated. He's just been very supportive, and like I said, he's been there when I want to talk, and not trying to. He's trying to give me my own space outside of that. When I was a junior faculty, kind of up through now, I guess there have been many periods where I've been asked to attend things that have actually been invitations that have been meant for my dad. So, as a junior faculty, if you get invited to give a keynote speech at a big conference, it's usually not normal. And so those would be instances where I'd say, I think you probably meant to send this email to, Rob Tibbs, not Ryan Tibbs. It happens still occasionally that that mistake gets made. Anyways, this was a very wandering answer to your question. Sorry, it was just I just was trying to give you the picture that I think on the whole it's been a huge positive for me and not at all negative.
Yeah, no, it's really interesting. A lot of the things you're saying, one of them, well, a couple of them. One is this idea of really kind of cultivating your own space, as it were, in terms of research questions you want to pursue and like what you're doing within the community. But then also the kind of trifecta you mentioned of doing within statistics very mathy stuff, very applied stuff, very computational stuff. Because I see among, I think, the papers we're going to discuss today too, those three prongs kind of coming out in your work in different ways. And I suppose I'm wondering how you think about, or how you kind of feel you cultivated your taste as a researcher and got a sense of what problems you wanted to work on, what that process looked like for you.
Yeah, it's a great question. I guess I don't see it as being, there's not like one answer that I can give, to be honest. I think it's somewhat driven by like what I find personally interesting in large part. And when I say interesting, I often use the word beautiful in a way that's I in this context I would use synonymous with interesting, but it's just a deeper, heavier word that kind of exposes one a bit more when you say the word beautiful. But um, I think that that's really the way I feel. A lot of problems I get drawn to because I think that they're beautiful and they deserve to be solved. Just fundamentally, there's something about them that I think is appealing in and of itself. And so some problems I work on them because of that motivation. Um, Other problems I work on because I think that they are central in some way, or that's my perception at least, that um, a solution to this problem would lead to things that people could do in the community. Um, and this is not a division that's, by the way, between theory and applied. I think it's cross-cutting. You can have theory that people pursue because they think that it's beautiful or fundamental in some way that's not that's different from it being a current kind of central concern of the community, right? So even within theory, you can have this division. And I know of people that I consider primarily theorists that I would say, at least externally, their motivation to me seems to be driven by one or the other. And with applied work and with computational work, I think it's somewhat similar. There are some computational problems that I think they're just very interesting to me, and I think that I get drawn to them because of that. And then there's a category of applied work that I think should be done because I think it's important, and so that's why I work on it. So it's just, it's a mixture of these two motivations. It's not binary. They're two axes basically. And yeah, I guess I just, I've never really had a very well thought out and specific agenda that is like, many years, that looks many years ahead. I kind of use these two axes to help me pick what to spend my time on. And in some ways, I've been lucky that that's led to, it's led to some good degree of productivity across the board. But it's but I don't have a game plan figured out. That's what I meant to say. It's not like I have, I couldn't tell you what I want to be doing for the next 5-10 years in any real kind of specific way. It's just these two things at play that are constantly kind of pulling me in to look at different problems.
I see, I see. That openness makes a lot of sense. And I think that's something I hear a lot of people kind of in the ML community commenting on, especially given where things are right now and the way it feels like almost everybody is chasing after the kind of large language model moment we're having right now. And I'm still hearing, especially within the academic community, a lot of voices calling to maintain that openness to work on different problems and not chase after the thing everybody is chasing on. And maybe there's this pragmatic sense of maybe hedging your bets because that's the most likely thing to result in a paper or something like this. But it's kind of just interesting to think about how different people consider that openness. Maybe one similar thing I'm wondering about in your case is I feel like there's a lot of, I guess, it feels like there's some obvious differences as somebody who's more familiar with the ML community coming and looking at the statistics community. For example, when I went and looked at your papers, they are on average like a lot longer than what we see in ML. I think maybe some of our papers have gotten longer, but this is more because we have papers with like stable diffusion and then you have 40 pages of pictures and not math. So that's kind of a fake length, which is very different. But I'm wondering a little bit, and after this, I think maybe we can dive into some of your specific papers, but just about how the statistics community thinks about maybe at a high level what sorts of disagreements there are within the community about directions that should be pursued, about knowledge production and what that should look like, about publication norms, because these are all things that I think the ML community continuously has disagreements on. And I'm curious what that looks like in your area.
Another great question. I guess I should preface it by saying I can't speak for, statisticians as a whole. So I think if every 10 people you ask this question that are in statistics, you'd probably get 10 different answers, with some overlap. And the other kind of caveat to give is that I think it's harder for me to see these differences because I feel that I've been intellectually, maybe not fully immersed, but at least partially immersed in machine learning for so long now that if you ask me what's the difference between, statistics and signal processing coming out of engineering or something like that, I think I'd have a better answer. Just because it's easier to see things when they're not kind of so close to you in some way. So, all that said, I think that's one and maybe important kind of difference to point out, and I attribute this to one of my former colleagues at Carnegie Mellon, where I was faculty for many years, who's Larry Wasserman. His name is Larry Wasserman. Larry used to draw, so he and I used to teach this course together called Statistical Machine Learning for a number of years, and it was a PhD course that was taken by students in statistics and also by the students in the machine learning department at Carnegie Mellon. And he used to draw this picture that's very simple, but I think it kind of tells, a decent story, which is that, in statistics we have kind of multiple arenas that people work in for in terms of their focus, but two very big arenas are prediction and inference. And by inference, I mean statistical inference. So prediction being, the problem of given some set of data, learning a map to predict, some unseen observation from some, let's say, covariates or features. And inference meaning the bubble that contains everything that you can do in order to infer statistical properties of distributions that from a set of samples. So, the simplest dichotomy would be, let's say I have data and I fit a linear model to predict y from x. So the model is linear in some features x to predict some response y. So that would be the predictive take. The inferential take would be, can I say something about which features are significant in this linear model? Can I actually give, under some assumptions, a confidence interval for their coefficient in the linear model, and so on. In statistics, we think of these as like two very big kind of areas of research, and maybe historically, actually, inference has been even bigger than prediction. In machine learning, it's exactly the opposite. So prediction dominates, inference is tiny, and historically in machine learning, inference may have been very, very small. And now I think it's grown in a way that people do talk about inference. They use the word uncertainty quantification. They don't think about inference in the traditional way statistically. But I think it has somehow emerged as maybe more of a focus. But still, if you grant me the rough picture, if we were to draw these two bubbles, prediction and inference in machine learning, and in statistics they'd be equal, or maybe even inference would be larger if you kind of incorporate the whole tradition of statistics over the years. So I don't think statisticians, that's not a disagreement. It's just a difference in focus, and I think that's probably would lead to my more kind of overarching answer, which is that statisticians have a different language for talking about problems than people in machine learning. I think that language came from the founders of the discipline, and then the people who contributed to the foundations over the years. Machine learning, has its own language. It overlaps in many ways, but it is different. And that language came from, I think, more from probably computer science, at least in various parts. And this is not a trivial thing. Like language, at least the way I think of it, language is not just the modality that you'd use to express ideas. It also shapes ideas. When we talk about ideas in given language, there's kind of a feedback loop. It shapes the way you think about them. It shapes the way that we work on things, and so it's led to different areas of focus. Right? We don't even have a language to express. If we don't have a language to express certain ideas, then there's no way to work on them. So that's the way I see it. I don't see them as being. I mean, if there are disagreements, I think they would be transient. If there are things that the communities actually disagree on that are technical, I think these are transient things that over time will kind of disappear. It's just more of the high level difference that I described.
That makes sense. Maybe one last question on this beat before we get into a couple of your papers, which is the language thing is so interesting to me, because I think that in machine learning, and I think since you've also been paying attention to it, you're kind of aware of this. There are so many terms that are thrown around within ML that have kind of unstable definitions, or there are debates over definitions. For example, people will talk about, say, robustness to distribution shift, which people will use kind of loosely, for example. And these are sort of ongoing, and many of them don't really come to resolutions. But I suppose when I look at statistics literature, not to say that I've looked at a lot, it does feel like there are maybe more stable senses of what things mean and how terms get deployed. And I'm wondering if that sounds correct to you, or how you kind of think about that stability in terms of different people, producing research and kind of communicating with one another within the community.
Again, with the caveat that both disciplines are so broad, and there's so much variation within each field that anything I say has to be taken as like, yes, there are millions of exceptions. So with that caveat, I think that's probably what you're commenting on as a reflection of the fact that statisticians are kind of more skeptical by nature, and there's a lot of iteration about whether something makes sense and whether or not something is the assumptions make sense and whether or not this way of looking at it is the cleanest or the most rigorous, et cetera, et cetera. Whereas I think in large part machine learning is much more of a doers community. You just you go and do something, and then you observe whether it works, and if not, then you fix it or you pivot to make it better in certain ways. Again, there are huge exceptions to both to what I just said within both communities. But if you grant that that's kind of like a high level, I think that we need both. Like we don't want all of science to be in one camp, right? I think it's helpful to have both, and I think that statistics has benefited tremendously by the energy in machine learning, and has kind of changed in certain ways to try to keep up with this energy that has maybe led people to be a little less skeptical and work in a little different way. And I'm not sure if it's statistics only that's rubbed off on machine learning, but maybe in part statistics has rubbed off other disciplines as well, where people bring in lots of rigor and produce foundations for machine learning as well. I mean, like I said, there's probably multiple disciplines contributing to that. So I think it's healthy to have both, and they both kind of rub off on each other. I'll just mention one kind of funny anecdote that I'll try to abstract away the specifics of who this happened to and where this happened to. It just kind of sums it up nicely. Is let's say some colleagues at a university in statistics would be approached by astrophysicists and would say, we have this problem. Here's what it looks like. We'd like to do this. And their reaction would be like, no, that's impossible. With what you have, that's not possible. And we can show you why. Your data doesn't support that. And it would just be a conversation about, you have to be careful. You can't just do that. It's not completely supported. The assumptions that you would need for this are probably not totally in place. Let's talk about it. Let's talk about alternatives. And the astrophysicists, in the meantime, were talking to some machine learning colleagues. And the machine learning colleague said, "Yeah, sounds good. We'll get you something by a couple of days from now." And you can imagine who the astrophysicists wanted to keep collaborating with after that, right? So it's these are two extremes. So it's but it's helpful to have both. That's I think that's clear.
Yeah, and I guess with that note that there are, as you said, many exceptions to these, I think that does feel right as kind of a pretty broad strokes characterization of things. Having spent, I guess, over 20 minutes on very broad questions, we do have a lot of papers to get through. And so I'm thinking maybe we should actually start with some of your more recent work. And in particular, there are a couple of papers about nonparametric regression that I wanted to talk about. And I guess both of them, well, one of them you suggested, but both are related to trend filtering. And I think that a lot of what's going on in these papers, some of the terms like splines, for instance, are things that are going to be very, very unfamiliar to our listeners. So I'm wondering if maybe I can throw the ball to you in terms of presenting some of the basis, some of the inspirations for these papers, and what led you to kind of start working on these problems and thinking about them as well.
Sure. And I mean, for what it's worth, we don't have to get through all the papers that you listed. So I have no concern if we just get through, some part of it in a way that's interesting to you and your listeners. So trend filtering, I guess to back up, there's kind of two things going on here, in what made this project interesting to me. And so I'll try to give the kind of high level of what those two things are. So this problem starts off, or this project started off in the simplest problem setting, which is one-dimensional nonparametric regression. So what that means is that you have a feature, and it's just one. It's a scalar, so it just takes real values, and so call it x. And I'm trying to predict some response y as a function of x. in such a way that is, I'm not assuming a parametric relationship between y and x. So I'm allowing the relationship between y and x to be, nonlinear and also not non-parametric means that we don't assume that it belongs to a finite dimensional parametric family. So for example, we don't assume that y is a quadratic function of x. We just might say that y is a smooth function of x plus noise, where that function has a derivative, and the derivative is bounded. That might be an example of a non-parametric assumption, and that's useful because it's a very kind of broad take on constraining the relationship between the thing you're trying to predict y and the thing you're trying to predict it from x. And it's still, in a setting like that, you can do something tractable. So it's kind of a nice middle ground. So that's nonparametric regression. The field of nonparametric regression is quite old. I would say that it's at least 100 years old. I mean, in some ways, it's at least 100 years old, and certainly the math technology is at least 100 years old behind a lot of the methods. And within the field, there are kind of two classes of methods that emerged in the 80s and 90s in statistics, and they go by the word locally adaptive versus non-locally adaptive. So what that means is as follows. Let's suppose you're trying to estimate some trend that tells you what the mean of y looks like as a function of x. And let's suppose that trend is it has smoothness that is not consistent throughout the domain. So what that means is that it's a very smooth trend for parts of the domain, and then it becomes very non-smooth. So it could be, for example, that you're modeling some response as a function of time, so that the covariate could itself just be time, and at some point in time you could see a change point in the response. So it somehow could jump, or it could oscillate, and then it could return to being smooth. A locally adaptive method is one that can adapt to the local level of smoothness, in the sense of fitting a smooth trend in some part, fitting a very non-smooth adaptive trend around this change point, let's say, and then returning to being smooth afterwards. That's actually very non-trivial to do in terms of constructing estimators that do that. And most methods in nonparametric regression that readers will be familiar with, or sorry, listeners will be familiar with, like k-nearest neighbors regression, kernel smoothing, reproducing kernel Hilbert space estimators, most spline estimators, they will not be locally adaptive. So they will actually not be able to accommodate big differences in the kind of local level of smoothness. And that's borne out both in theory and in practice. So they don't work practically or theoretically without significant modification. So for a kernel smoother, maybe if your listeners are familiar with what a kernel smoother is, a kernel smoother just takes local averages of let's say the responses, the y points that it sees, and any neighborhood of a point that it's trying to predict, and then weights them in some way with a kernel function. For a kernel smoother to be locally adaptive, you'd have to train the bandwidth in the kernel smoother to be a varying function of x. So you'd have to make the bandwidth very large when the function's smooth and very small when the function's non-smooth. So that's a very complicated thing to do. If you imagine trying to fit an estimator whose bandwidth is also varying with the covariate, it's a very kind of complex estimator to be able to fit in practice and also to be able to study. So locally adaptive methods are, I guess this would be one example, a kernel with a kind of varying bandwidth. Locally adaptive methods are a class of methods that are able to accommodate this local difference in smoothness. I became interested in them because of some papers that I was reading in grad school that seemed to me to be kind of like an analogy to the lasso, essentially. They were the kind of non-parametric functional versions of, related in some way to the lasso in regression. So I just was interested in the lasso, and I kind of saw these papers and was reading about them. So that's the one axis that I said, which is they are locally adaptive, which kind of sets them apart from most things that people use, and they can therefore be useful in problem settings in which the trends are not kind of are not homogeneous. The second difference is in this thing called so turns out you can pose non-parametric regression problems in continuous time or in discrete time. And what I mean by that is you can try to estimate a function, like a whole function that dictates the mean of y given x, or you can just try to estimate the function values at given points. So like estimate the mean of yi given xi over a set of samples I equals 1 to n. And I would refer to those as continuous time and discrete time. And that's the other axis somehow that, signal processing and even econometrics actually has evolved focusing on discrete time estimators. Statistics and applied math have evolved focusing on continuous time estimators. And so trend filtering is at this intersection where it's locally adaptive and discrete time. So that's the way I would kind of categorize trend filtering. And what I became interested in is kind of trying to connect it to things that people had done in locally adaptive continuous time nonparametric regression. And that was kind of the start of my work on the problem. And then we kind of looked at it in broader ways outside of the one-dimensional setting, trying to do it on more complicated domains. And I'd say that the takeaway maybe for your listeners, if that kind of high-level kind of categorization didn't stick, is that it's a computationally efficient locally adaptive estimator. So because it's in discrete time and because of its particular formulation, it turns out to be more computationally efficient than many other locally adaptive estimators. So it's something that is whose computation brings it closer to simpler estimators that we would fit like traditional non-locally adaptive estimators, but it's able to do more with just a little bit more expensive computation in the sense of adapting to trends that are local. And the last thing I'll say about it is that there's actually an interesting connection to neural networks. Neural networks are an example of a locally adaptive non-parametric regression method. That is not the way that people in machine learning would think about them, but I think it is a fair kind of categorization. They are able to adapt at a very local level to trends. They do not use parametric models for the trends. And there's actually even a connection between trend filtering and neural networks that is not just kind of conceptual. There are neural network architectures that solve problems that are very similar to the problem that defines trend filtering. So you can actually show that maybe even in the simplest setting of, again, one dimension, there's a common kind of ancestor in terms of the optimization problem they're solving. But then we choose to parameterize that problem, or we operationalize a solution to that problem in different ways.
One specific question I had with trend filtering was this detail you bring up in the paper about one feature of filtering being that it falls into what's called this analysis framework with respect to problem formulation. And you distinguish the analysis and synthesis frameworks. And I'm wondering if you could elaborate a little bit on what those are and I guess what it means for something to fall into one or the other with respect to problem formulation.
Yeah, so I credit people in signal processing with those terms, which is where I first heard them. And there are a small number of papers in signal processing that try to talk about this as maybe the main focus of the paper. But or maybe I think there's a small number. Maybe there's many others I don't know about. But the kind of gist of it is this. Let's suppose, again, we're in the non-parametric setting, and I want you to construct an estimate for the trend that dictates the mean of y given x. The synthesis approach is a bottom-up approach. where you specify a set of basis functions, which you can think about as they give you kind of a set of atoms that you combine to get some kind of global behavior. So a basis function could be, for example, just what people in machine learning call a ReLU. So I'm going to allow my basis functions to be, or what people call a hinge function in other literatures, 0 at some point in time, and then activate as a linear function to the right of some knot. And I'm going to add together all combinations of basis functions of that form over all possible knots with coefficients. And that'll kind of form the class of estimators that I'm considering. So the basis functions or the atoms would be ReLUs, right? The analysis framework is very different. I don't specify a set of basis functions. Instead, I start off with like kind of a complete parameterization. I allow my function to be anything. But instead of specifying the trends I want to see, I specify the basically a penalty on aspects of trends I don't like. So I start with everything and I whittle it down. I whittle the set of kind of possibilities down by penalizing behaviors I don't like. And so as an example, I could say that I don't want the derivative at this point to be very large. This point meaning like a specific point. And then I could integrate over all points to say I don't want the absolute value of the derivative to be large in an average sense over the domain. That's just telling you what you don't want in the estimator, rather than saying I want the estimator to be combinations of functions that look like this. And it turns out that those are, so if I actually say that I don't want the second derivative to be very large in an absolute sense, integrated over the domain, then that turns out to be equivalent to specifying that the set of basis functions are ReLUs. It's not obvious why that's true, but those turn out to be the same problem formulation. So you have these aspects where both synthesis and analysis can kind of coincide to give you the same eventual problem formulation, even though I didn't motivate it the same way. It's just that in some problems you can invert one formulation to get the other. So it turns out we can invert either problem formulation that I described earlier to get the other. The reason I like the analysis formulation in the trend filtering paper is that it's, at least in some ways, it allows you to specify estimators in problems for whom you cannot specify a set of basis functions that are very natural. So on some domains, it could be hard to specify basis functions at all. But it would not. It could still be possible to specify a penalty on the types of behaviors you're trying to see. So graphs are one example of the domain. So if my x's correspond to nodes on a graph rather than points on a line, then it's kind of hard to think about what a basis function looks like on a graph, right? If I just gave you an arbitrary undirected graph and I said, give me a set of piecewise quadratics on the graph that are continuous and have continuous derivatives, that's not really well defined. We don't really know what that means mathematically in some sense. We'd have to embed the graph into Euclidean space in order to be able to somehow even make progress on that. But I could think about penalties that try to incentivize behaviors like that on the graph. So I could take differences between neighboring nodes, which kind of acts kind of like derivatives. And I could take differences of some order and I could say I don't want those differences to be very large in absolute value. And that could kind of lead to behavior that is like a quadratic. And that's why in various problems that we've worked on, the analysis framework is maybe more user-friendly. It allows you to construct estimators in ways that you couldn't otherwise. Neural networks, by the way, they're kind of a very kind of specific take on synthesis, which is that you work on in a synthesis framework through function composition. So I don't specify I mean, we don't specify what the basis functions look like globally in the sense of, I don't tell you that, you should be this linear combination of these functions of x. Instead, I specify that through kind of composition of simple functions. But in the end, it is a synthesis framework, right? Because we do construct basis functions, they're just complicated. So we don't tend to think about neural networks as, being in the analysis framework. But what I was saying a little bit earlier is that there are analysis takes on neural networks. You can write down problems for which you're optimizing over functions, not constrained to be compositions of ReLUs, just functions. And you have penalties in place that move you away from those functions expressing certain behaviors.
I was thinking about regularization on that front.
Exactly. And you can prove that those problems are solved by neural network architectures. This is not my work. This is just work that has been in the literature in the last several years.
Maybe using the different frameworks as a segue into your other paper on nonparametric regression we had on the front. You have this very, very interesting paper on divided differences, following factorials, and discrete splines that also kind of looks at trend filtering. But I guess as I kind of, and I guess I'll admit, I like this was a very long paper that I think I didn't get to go into as much detail as I wanted to. But it was really, really interesting. And there's like lots of cool math in here. And you're looking at this thing called a following factorial basis. And you're kind of building up some of the like properties of what's going on here. And then you eventually connect it to trend filtering. And I guess I'm wondering maybe about some of the motivations of this paper. I guess it strikes me as something that could be looked at from what you were saying earlier as like, this is just a really cool, beautiful thing to look at mathematically. But I guess I'm wondering how you kind of thought about some of what's going on in this paper.
Thanks. Yeah, I was interested in it initially just because I thought it was interesting, and it was in the deserves to be solved category, but somehow there were connections between trend filtering and this class of functions called discrete splines that I had kind of come upon that also appeared in some previous work by other people, and I was trying to kind of see how far I could push that because I thought it was interesting. And this paper ended up being kind of a mixture of a review of splines, discrete splines, and what we know about them, and then also some extensions on the kind of numerical analysis and the numerical approximation properties of discrete splines, and then connecting it to trend filtering. And it is very long. It took me a while to write it, so I don't blame you for not getting through it. This was yeah. So maybe the kind of couple high level sentences about it is that splines are a space of functions that people in math have been working with for over 100 years that are a very special set of piecewise polynomials. So piecewise polynomials, there are piecewise polynomials that are essentially the smoothest piecewise polynomials you could hope for, because if they're piecewise polynomial of degree k, so let's say cubic, then they are the subspace of piecewise cubic polynomials that is continuous and has continuous first and second derivatives. So where the pieces meet, the polynomial can't change in terms of the endpoints it has to meet, and its kind of rate of growth has to meet, and its curvature has to meet. So they're very smooth piecewise polynomials, and people in math like them because they're smooth enough that somehow they are, that's useful for a variety of applications where you want to estimate smooth functions, but they're flexible enough because in the cubic case, you're allowing the third derivative to change. Not the second or the first or the function itself, but the third derivative can change different parts of its domain. It can actually be quite expressive as a mode of functions for estimating trends. So that's a spline, and we have estimators in statistics that are based on that. One's called the smoothing spline. One's called the locally adaptive regression spline, it's the locally adaptive version of the smoothing spline. It kind of, as I told you earlier, people in statistics kind of realized that was an important direction to work on. Trend filtering relates to all of this in that it uses these kind of same formulations but in discrete time. And to make that precise, I started studying this function space called the space of discrete splines. And it turns out that there has been work done on discrete splines that I just was kind of learning about in putting this paper together that seems to have been really a minority in math in the 1970s. But it's really useful because it leads to very computationally efficient methods, trend filtering being one of them. And the way you think about a discrete spline is that you take the same properties you ask of a spline, but you replace the word derivative with discrete derivative. So I replace, the simplest notion of a discrete derivative is take the difference between a function at 2 points and divide by the difference in the inputs at those points. So just the slope. Yeah, exactly. And that's actually called a divided difference to be kind of specific about. There's many notions of discrete differences. This is called a divided difference. It goes all the way back to Newton, actually. So Newton was interested in divided differences. I want to make sure I get this right. I think that Newton was interested in divided differences even before a lot of calculus was being developed. So this is even pre-calculus somehow.
Interesting.
Yeah. So for example, there's something called Newton's divided difference interpolation, which is like a discrete version of Taylor's Taylor expansion. So Taylor expansion, I can take a function and I can expand it in terms of polynomials and derivatives. I can do the same thing. I can expand a function in terms of polynomials and divided differences. And if I hope I have the history right. I think this actually predates Taylor expansion. So there's basically the point is that there's an entire set of machinery that has been developed in math for talking about discrete analogs to things like derivatives. And if you take a spline and you substitute the word derivative with discrete derivative, you get something called a discrete spline. And so you can start developing properties of discrete splines as a class of functions and methods that are based on discrete splines in a way that's very parallel to the kind of world of splines. And so that's what this paper tries to just show, that we have these things in splines, we can do these things in discrete splines. And again, to the credit of many people in math, this is not something that is new to that community because they've been doing it for 50 years. But I think at least in statistics, we don't really have many estimators that are based on discrete splines. So the fact that trend filtering happens to be one of them, and it wasn't the original motivation for the method. And the original motivation for the method which was introduced by people who were, before I became interested in it. It was just from first principles. So the fact that it happens to be, connected to discrete splines was just a happy coincidence.
So in speaking about, say, starting from like the difference between divided differences and derivatives, or between using those for things like Taylor expansions, for instance, when we do, I guess, your ordinary Taylor expansion, depending on the order of that expansion, we can say something about how good of an approximation this is to your original function, and thinking about then stuffing in differences instead of like exact derivatives, that's going to have some implications, I would suppose, for the approximation, right? And so when we look at discrete splines, I guess what I'm thinking about is that difference between, you mentioned computational efficiency being like a desirable property here, and then that trading off with approximation. And so I'm wondering if you could talk a little bit more about like that aspect of discrete splines and maybe some of how that came out in this paper.
Yeah, that's a great question. So I think that there is a field that works on this kind of discrete calculus, and there's probably answers to what the approximation error looks like, that are fairly precise. And I think the book by Schumacher, he has a book called Splines: Basic Theory. There's a chapter in that book that's all about discrete splines, develops a bunch of approximation theory. So I would imagine we could find some answers in that book. When it comes to using these as kind of the basis of estimators for statistical trends, the way I think about it is that both splines and discrete splines are approximations to whatever the function is you're trying to estimate. So they incur somehow an equal approximation error, because discrete splines are just as expressive as a function class as splines. So I can define a discrete spline over a set of knots. That function class has a certain dimension. That'll have the same dimension as the class of splines over those same knots. And they're equally expressive. They're just capturing trends in a different way. One is requiring smoothness in a kind of continuous sense. The other is requiring smoothness in a discrete sense. And so, we have results that say that if f is a function that's, has so many derivatives, and let's say if I integrate, it's the absolute value of its second derivative or the square of its third derivative or something, some notion of smoothness like that. And it's let's say at most 1 or at most some constant. Then I can find a spline given, let's say, n knots that's at least this close to the function that you're trying to estimate. That's an approximation theory result. Discrete splines should in principle satisfy the same approximation bounds in terms of the order of approximation and the complexity of the function you're trying to estimate. Like I said, if the integral of the absolute value of some number of derivatives of your function is some value c, then as c gets larger, I'm allowing the function to be more complex. And I think that discrete splines and splines should lead to the same approximation rates in the complexity and the number of knots. So I don't think of it as being more of an approximation than splines. I think of it as being a different approximation than splines for that reason.
That's a really good clarification. I think at this point, so I actually really wanted to talk to you about conformal prediction. And there's a series of papers you have on this under the distribution free inference section. And a place I kind of want to start, though, is with some initial motivations. And part of why I particularly want to talk about this with you is there's been, it seems like some discourse around the blogosphere around conformal prediction and prediction bands and their use. I think one of your colleagues, Ben Recht, has been writing a series of blog posts about sort of quantifying uncertainty of ML models and has, I think one of your papers actually deals with some of the issues he has with conformal prediction as a way of doing things. But I'm wondering if we can start with some kind of initial motivation for how we get into conformal prediction, like why something like prediction intervals for quantifying the uncertainty of ML models, why this is useful, what we do with prediction bands, and then kind of getting into conformal prediction itself.
Sure, I'm happy to talk about it. So I just to kind of pay tribute, as I tried to do a bit with splines, to the history. Conformal prediction as a method was developed by this person's name is Vladimir Vovk, V-O-V-K, who is currently at University College London. He's a computer scientist, and some of his collaborators as well, Glenn Schaefer and Alex Gammerman. And I think he also credits Vladimir Vapnik in his book for some early conversations about it, although Vapnik is not, Vapnik of SVMs and VC theory, etc. I think that they, were friends or at least, acquaintances, and he credits Vapnik with some kind of early inspiration. Now, and interestingly, Vladimir Vovk was the last student, Ph.D. student of Kolmogorov. So he has a very kind of interesting and kind of, like intriguing legacy there in terms of the work that he's been doing. So they developed this method in the late 90s, I would say. They continued working on it he still works on it very productively. I mean, he's been a huge contributor and, the main kind of driving force behind conformal for many years. It wasn't until the 2010s, I want to say, that it became kind of on the map in statistics. And two of my colleagues at Carnegie Mellon, Larry Wasserman and Jing Lei, were the first two that I know of to work on it in statistics, and I learned about it from them. So I started working with them after they had already written a few papers. And then, I think it kind of had a bit of a slow growth in statistics for maybe the next 5-6 years. And then at some point, it became extraordinarily popular in machine learning. And it feels to me like it was overnight. I don't know how it happened. It's not due to me in any way. I think it's probably due to other famous people who write papers about conformal prediction, or it could be that this is the way things happen in machine learning, and it's always hard to kind of, associate causally, why kind of things, get popular. It's just the ebb and flow of research. Some things get popular, but I think people in machine learning like it because it's, in many ways, and I'll try to be careful about this, it's very light on assumptions, as opposed to traditional inference techniques in statistics, which are, many of the traditional inference techniques are very heavy on assumptions. So as far as trying to do things that are distribution lean, like assume a few things about the distribution, or theory that is distribution lean, or assumption lean, this is like a good area. It's not perfect, and I think that there are many ways in which people either oversell or don't realize the limitations of what Conformal is doing. So I'll try to be kind of careful in spelling that out. But that's the history, at least. Oh, and one more thing I'll say in terms of the history very quickly is that it connects very much to ideas that are very old in statistics. So in particular to permutation testing and to the idea of constructing confidence intervals by inverting hypothesis tests. So one way of thinking about conformal prediction is to invert a hypothesis test in order to get a prediction interval rather than a confidence interval. And I'll try to explain like roughly what that means. But it connects to those ideas in statistics. So conformal prediction in its most basic, maybe instantiation, and the one that's the simplest to operationalize, works as follows. You have some data, labeled pairs, x and y. X is the feature, y is the response. And I want to not only predict y from x, I'd like to get a prediction set for y given x. And so you asked why we might want that. I think actually the best people to ask that question are the people who work in particular domains. Because that answer, they're going to have a different answer depending on the domain. And I don't think that, somebody who's working on kind of, methods that are out of context or theory that's out of context can give you an answer that is as appealing or as kind of, substantiated in terms of what the discipline's actually trying to do as somebody who works in the particular discipline. So I can just give an example in an area that I work in, which is epi forecasting. So if we're trying to predict hospitalizations as a function of covariates and time, it's very different to give a policymaker a prediction that says, I think that you're going to see, in your county, 1,000 hospitalizations over the next week, which would be a huge number for, at least for counties that are not LA County. But, for normal sized counties, that would be a huge number. Or to say, I think it's going to be 1,000, but it could be as small as 10, and it could be as large as 10,000. And that is, and I make that statement with 90% frequentist coverage, in the sense that, if I were to give you these predictions over the course of this season, I expect that 90% of my intervals that I give you will actually contain the hospitalizations that you see. That's very different than them saying, I think that's going to be 1,000, but it could be as low as 800 and as high as 1,500, with the same prescribed probability. And the reason that, a policymaker might want a prediction interval is that if the lower limit with some decent probability is of this interval is actually, let's say, a large number, then they may actually want to do some kind of preparation. They may want to, if let's say this is a 3 or 4 week ahead hospitalization forecast, they may want to say, okay, take people off ventilators that are not critical. Don't let staff go on paid leave. Cancel all elective surgeries. Do everything we can to kind of make the hospital prepared for the load we are anticipating that we're going to see. And again, I'm probably not the right person to ask even in this context, because I'm not a policymaker. But this is the kind of thing that I think you would get different answers in different disciplines. So okay, so now just generally about conformal prediction. Conformal prediction in the simplest kind of instance is, again, if we have x and y, you have a big training set. Let's say you, as the data scientist, tell me that you have a prediction algorithm that you like, a neural network, a random forest, whatever it may be, that you think based on either past experience or problems that you've solved that are similar to this one predicts well. So what conformal prediction does is it basically serves as a wrapper on that prediction algorithm to take a point prediction, which means that at a future x it produces a single guess y, into a set of plausible y's. And the way it does that is by, here's the simplest way. It divides the set into two parts, the training set in two parts. One I call the proper training set, the other I call the calibration set. On the proper training set, I run your method like random forests. On the calibration set, I have your calibration set, which is, again, labeled pairs, x and y. And I have an x at which you want to make a prediction and no y associated with it. And what I do is I just posit a value of y associated with that x. So let's call that the test point, x, and then I put in just a guess for y. I then throw that into my calibration set, and I ask, how does the error look on this test xy relative to the errors on the other calibration points? Is it very large? Is your algorithm committing a very large error? Or is it committing an error that's kind of, roughly concordant with the errors on the calibration points? And I can do that by just saying that, I want the error on the test point to be within the, 90% of the smallest errors that I see overall in the calibration set. I can use any error metric I'd like. It can be squared error, if it's classification, it can be, binomial deviance, it can be whatever you'd like. So whatever prediction algorithm you like, whatever error metric you'd like. This is just a meta kind of routine that I perform. And my prediction set is the set of all guesses, little y, for the test point, for which the error associated with the test point was within the 90% smallest, fraction of errors in the calibration set. So now you can see it as inverting, basically, it's inverting a hypothesis test. The hypothesis test is that the error on the test point is basically the same distribution as the error on the calibration points. That's a hypothesis test. Those two distributions are the same. And I'm accepting all kind of guesses for the test label, for which that is my hypothesis test does not reject, for which I don't have evidence that that's false. And that becomes my prediction set. And it turns out that you can do this without having to computationally iterate through values, little y, in code for a variety of error metrics. So if the error metric is like a squared error or anything based on the residual, there's a closed form for this that's based on quantiles. So that's the way you'll often see it written. But that's the way you think about it. It's just, that's where the name comes from, as far as I understand too. It's the set of all test values for the response such that the error on the test point conforms with the error on the calibration points. And the reason that's a fair comparison is because all of these points were not seen by the training at the training stage. So at the training stage, it did not see the calibration points. It did not see the test point. So all of these are out of sample with respect to the original model fit. That's why I'm doing the splitting in the first place. So it's truly, in that sense, a fair comparison. I can tell you what I think maybe the biggest crutch of conformal prediction, or there's two biggest crutches, if you'd like me to say, or you can ask questions about it. So the positives are, for any number of samples, n, for any algorithm, for any error metric, which we call a score function, usually in conformal prediction, and for any distribution that governs x and y. As long as you have i.i.d. samples from some distribution, as long as your data is i.i.d. from some distribution, across the whole training set and at test time, then the probability that your conformal set will cover the test y is at least the nominal level, so whatever you prescribe it to be. So it's guaranteed to be 90% if you pick that as the nominal level. So that's the strength. There's no asymptotics, there's no assumptions about So if I'm fitting a linear model as my algorithm, I'm not assuming that the data follows a linear model. It's just that it could follow anything. I could choose to fit a linear model. That's the strength. The crutch of conformal prediction is twofold. The first is that it assumes that the training data and the test data are all i.i.d. So it does not accommodate, at least in this particular version I told you, any kind of distribution shift, either within the training set, which could happen if it's time series, right, as an example, or between test and training, which could happen in many practical applications where I'm training a model on one population and then I go out and use it in the wild on a different population. So conformal prediction in the version I just told you says nothing about these. It's not that there isn't theory that has grown to kind of describe what happens there. It's just that the simplest version does not cover those cases. The second crutch is one that's well known. Everybody knows. I mean, at least everybody I should know that conformal prediction is meant for i.i.d. data in its original form, or slightly weaker than i.i.d. exchangeable sequences, which just means that the probability of seeing the data in any given order is the same. It's weaker than i.i.d. The second crutch is this one, which is maybe less well known. The coverage that you get, the guarantee is marginal over the feature, which means that it's an average coverage over features values that you would see at test time. It's not conditional on a given feature value. So to ground that in an example, this is an example that I like to give, but I credit it to my co-authors on some of the papers that I've written, Rina Barber, Emmanuel Candace, and Aditya Ramdas. We've used this example internally as motivation for a lot of the kind of, a lot of the stuff that we do. So it's a shared example with them. Let's suppose that you're a patient and you come into my office, I'm a doctor, and you say, doctor, how long do I have to live? And I give you a conformal prediction interval. I say, I take your features, I run them through my random forest, I conformalize that, which means that I apply conformal prediction by separating out training and calibration, etc. I give an interval, which is, I expect you to live between, I don't know, let's just say 4,000 days and 5,000 days. I have no idea if shortchanging you. It probably sounds like you should live longer, but let's just say 4,000 to 5,000 days. And you ask me, okay, what guarantees do you have for that? And my answer to you is that, over all people that come into my office, all patients, I'm only wrong 5% of the time, which means it's a 95% prediction interval. It has 95% coverage. Your immediate response would be, I don't care about people that come into your office. I care about me. I care about my features. So given that I have these genetic markers which you measured, I have this diet, I have this demographics, I have this family history, etc. What can you tell me for these features? And I can't say anything about that at all, because conformal prediction does not guarantee us coverage conditional on the feature that I'm going to be seeing at test time. And it's impossible in a certain sense to make prediction sets that have conditional coverage on every possible feature value that you'd see without distributional assumptions. So we can show that that's, in a sense, an intractable problem. Anyways, those are the two things. It's an average coverage. Think of it as average case over the features, and it requires i.i.d. samples. Both of those things have been worked on by the community, and there are extensions in both categories that give you things that are approximate conditional coverage, or getting you closer to conditional coverage, or that allow for deviations away from i.i.d. But those aren't foolproof. It's not like they'll solve every problem. They solve some problems. And so it's, it has less of a sweeping nature than the original conformal prediction kind of theory, which says that, it's very broadly applies to all these problems. Once you move into conditional coverage, once you move into the literature on how can you extend conformal to allow for local coverage or conditional coverage, or how can you treat non-i.i.d. problems, you'll see that it's, the solutions are not completely general purpose at this point. They solve certain problems, and they're designed to solve certain problems. It doesn't seem, at least to me, to be very realistic to expect that we can get totally general purpose solutions outside of those two cases. And in the case of conditional coverage, as I mentioned, we know that it's impossible in some sense.
I want to ask about a couple of sort of fundamental issues and concerns that have been raised. And I guess I again have to credit Ben Recht for talking about a couple of these. But one of them that you pointed out was the nice thing about conformal prediction is regardless of things like your predictor, your scoring function, you can kind of get the same guarantees you're looking for. And when Recht was writing about this, one thing he said was that from his perspective, one should actually be worried that you get the same probabilistic guarantees with conformal prediction, regardless of the scoring function, and that this maybe almost invites you to use garbage prediction functions. And I'm wondering if that's kind of something you've thought about in studying conformal prediction, or how you think about a worry like that.
Yeah. So I haven't read Ben's blog, so I can't comment on anything else than what you tell me. So it's kind of a conundrum. Let me tell you, the conundrum is even somehow a little bit more finicky than what you just mentioned. So there's actually an upper bound on coverage. Okay, so it's not just that we know that the coverage is at least 90%. It's actually, in kind of typical cases where the score that you're using is continuous in the sense that there are no ties between the scores on the calibration set and on the test set. We actually know that the coverage is upper bounded as well. So if you have 100 calibration points, then let's see if I get this right, then the score is at least, so the coverage is at least 0.9, and it's at most like 0.91, basically. So there's a very tight, the coverage gap between what you achieve with conformal prediction and what you're trying to achieve is 1 over the number of calibration points, essentially. So if it's 100, then that gap's 0.01. So you can get very close to 90% coverage with a large calibration set. So it's not just that you can get at least 90% coverage, you can get almost exactly 90% coverage. And that's strange because you can do that with any algorithm. And here's here's the flip side of it, is that that's just somehow one side of what people look for when it comes to prediction sets in practice. The other side is the size of the set, or the length of the interval, in the case that it's an interval. The better the algorithm I use, the smaller the prediction interval will be. This is something that's substantiated by, theory and experiments. So if I have something that predicts better, then I'll get coverage and I'll get a small interval. If I choose a garbage predictor, I'll get coverage, but I'll get a big interval. So I would say that if somebody doesn't know that, then it may incentivize them to be lazy because they just think that anything works. But once you tell that to somebody, anybody who is using this downstream would not want an unnecessarily large prediction interval. I want the interval to be as small as it can be, subject to covering. And therefore, I would do everything I would usually do in a machine learning workflow to try to optimize predictive accuracy. I would tune hyperparameters. I would move between models, change architectures, whatever it would be. So I think that's hopefully a pretty reassuring answer to this concern.
Yeah, I think so. The other thing I wanted to talk about with this was the sorts of assumptions we make. So you talked about i.i.d. and then weakening i.i.d. to exchangeability. And I guess with like i.i.d. in general, the independence notion is something that's known to be a pretty strong assumption. But then exchangeability, as you said, we can kind of weaken this to something that's broadly like the order of things doesn't really make a difference for us. And that's still kind of like a limiting assumption and is something that can be broken in a lot of real world scenarios. So one of the papers you suggested in this was a 2023 one you worked on with some other folks about conformal prediction beyond exchangeability. And again, there is that motivation that when you're deploying predictive models in practice, that's something that's going to be violated a lot. And so I'm wondering if you could talk a little bit about, for listeners, just the ways in which exchangeability gets broken and how you think about trying to, I guess, cope with the demands of we can make all of these statistical guarantees, but only given certain assumptions about the way the world works, and how you deal with that.
That's a very good question, and I agree that exchangeability is a very strong assumption. I think it's weaker than i.i.d. And they actually relate in some ways that beyond the fact that an i.i.d. sequence is exchangeable. But in any case, it's a pretty strong assumption. So I would say that there's been a lot of work in conformal prediction over the last 4 years, 5 years in trying to accommodate non-exchangeable data sequences. And in my view, it's divided into two cases. What I would call the batch case and the online case. And they're very different. And in some sense, it's worth talking about them separately. In the batch case, what that means is that you just give me some set of data, training data. It has endpoints, and you tell me that I will receive a test point. And I'm trying to produce a set that's based on that endpoints through the method that I already described earlier, let's say, that has a probabilistic guarantee once I see the test point. And let me immediately tell you what the online goal is so that I can at least differentiate it before I talk about the methods. In the online case, I think about the test data as streaming, being a sequence. And at every time, let's just say t, I construct a set based on the points I've seen. And then I measure whether or not the set covered the point that I see at time t+1, which I didn't get to see when I had to construct the set. And instead of asking for a probabilistic guarantee that will cover at time t+1, I instead ask that the frequency of coverage over the sequence is large. So it changes the statement from being about a fixed training set size, a single test point, measuring success with probability, to being an infinite sequence where I keep receiving test points, measuring success with empirical coverage over the sequence. So these are two different ways of thinking about the problem. They're very different in terms of the solutions that are available. And in many ways, the online case, we can do things that I think really are kind of completely agnostic to distribution shifts. Well, they're not agnostic to it in the sense that, let's just say the theory accommodates completely arbitrary distribution shifts. The methods shouldn't be agnostic to that. They should adapt to that. If the methods were agnostic, then they would be bad. But the methods can still accommodate completely arbitrary distribution shifts in the online setting. But it's because we're not asking you at time 100 to cover at time 101, right? We're asking you to cover some on average along the sequence. So it's a different way of setting up the problem. In some time series forecasting problems where it's like a long horizon, very long, let's say forecasting test set, you might live with the empirical coverage along the horizon. That might be okay. In another time series forecasting problem, or just in any kind of particular machine learning problem, you might actually not get more data, or you might not want to think about future data. You might ask, with the data I have, how well will I do, next week? And then you can't think about it as an online problem. You need to think about it as a batch problem. So in the batch setting, there are methods that try to weight the calibration set in such a way that you place different weights on the scores from different calibration points, not even weights. So remember when I say you compare the test error to the calibration errors, or the test score to the calibration scores. I could compare it to some kind of reweighting of the calibration scores so that the points that I think are more representative in the calibration set of my test distribution receive higher weight, right? And I would downweight the points that somehow I think are less representative of my test distribution. So there are a couple of methods in that vein that I've worked on. I think it's fair to say that they're proper extensions of the theory of conformal prediction, because, I mean, this is work with the same set of collaborators that I mentioned before. They're proper extensions because they reproduce the results in the i.i.d. case. But they show you that if the data is not i.i.d., then you kind of suffer a loss in coverage that's proportional to the weight you assign on a given calibration point times some notion of difference in the distribution of the that calibration score and the test score. So if you had put high weights on the calibration points whose distribution was similar to the test point, then that would incur a smaller loss in coverage because the distance between those two distributions measured in total variation distance in our case would be low. If you guessed wrong and you put high weight on calibration points that were dissimilar in distribution to the test point, then the loss in coverage would be high. So this theory that we developed kind of quantifies this in some way. It's not exact, it just gives you a bound on the loss in coverage in a way that also that bound will equate to 0 in the i.i.d. case. So that's why it kind of reproduces the conformal theory in the i.i.d. case. That's not an immediate practical recipe for people, solving all distribution shift problems in batch, right? You have to have some sense of what the distribution shift is. If I can guess right, and I can imagine that distribution shift will be in directions that make these calibration points more similar, and these calibration points less similar, then I can weight the kind of construction of the conformal prediction set in such a way that I have good coverage. But it still is, I think, a pretty, it's a very open-ended problem on how to do that. Well, certainly in general, and I think it remains to be shown that in specific problem instantiations we have practical schemes for doing that efficiently. Some of the work I'm mentioning just kind of showed that this was a general kind of idea that could be applied. In the online case, it's very different, as I said. So you can do, it turns out, quite simple things, and you can get coverage along a sequence, empirical coverage along a sequence, pretty generally. And I've worked on this. Some others have worked on this. So there's kind of an interesting literature developing there too. And the original method, I'll just describe it, which is not mine. I'll describe what it does there. It under the hood, it keeps track of a working error level. So let's suppose you tell me I'd like 90% coverage. Here's my method. I like to run random forests. I like the error metric to be squared error or whatever. I'd like 90% coverage. Along the sequence, I actually internally, in running conformal prediction, I turn a knob, which is the knob that I'm using in order to seek, let's say I call it my working coverage level. So in order to achieve 90% coverage, if your algorithm is miscalibrated, I may need to actually query it for 98% prediction intervals, right? So I may need to actually ask it for more coverage with the understanding that actually it tends to undercover. And the method that, one of these methods that was the first method developed in the online case, it just does this in a very simple way. It tries running the algorithm with the nominal error level, so let's say 10%, and if it doesn't cover, it makes the nominal error level smaller. So it asks the algorithm to commit 8% errors, let's say. And if it doesn't cover, it makes it smaller again. And when it covers, it makes it bigger. And when it doesn't cover, it makes it smaller. So it's kind of like an adaptive control that's run on top of the algorithm. And what you can show, it's very simple, is that this will, in the long run, produce prediction sets with empirically 90% coverage or empirically 10% error. So it's I'd say that there are pretty satisfying answers in the online case, and there's others that do, you know, maybe things that are extensions of what I mentioned.
Yeah. So I think I want to ask you a last question on conformal prediction and then maybe move to a final paper I have some questions on. And I think that's one that I'll have some interesting takeaways. Here, I guess a lot of what you've discussed, I guess the batch case for conformal prediction and then some of the negatives about it do suggest kind of immediate avenues for future research. Things like how can we deal with the weakening of assumptions we might make. And I guess, kind of having worked on this recently and having that recent paper on conformal prediction beyond exchangeability, what the most important immediate next directions feel like for you when it comes to conformal prediction?
I'm going to have a bit of a controversial answer here. I mean, not really controversial, but I think that what we've seen in machine learning and in statistics recently is an explosion of effort to continue to develop conformal prediction methodologically in ways that extend it. And I don't think me saying, that we should work on X or X prime or Y prime is going to change the intensity with which people work on conformal prediction. I think they'll continue to develop it in various directions, and hopefully some of those, I think they will be, steady stream of work on the non-i.i.d case and the local coverage improvements and so on and so forth. If you had to, ask me for what I hope people would focus on, I would choose something slightly different, which is to focus on integrating conformal prediction into practical pipelines, because I think that's where it's been a little bit underdeveloped. I think that the method is kind of overdeveloped relative, saying it differently, the method's overdeveloped relative to the practical success that it's had. It has enormous success in simulations. It has enormous success in theory. It has enormous success in terms of being, being fruitful as an area for people to extend it. I don't think I know of a ton of examples of people sticking in prediction pipelines, figuring out its operating characteristics, whether or not the set sizes are even practically actionable for the decisions they're trying to make. If not, playing with all the knobs that they have access to in order to improve their prediction sets, and even like connecting prediction sets to decision making. As you asked me as one of your first question, I'm not clear that there's a general way to do that. So I think that that's something that just needs to be borne out through experience and practice to see what that looks like. So I think that'll happen. I think that the way that fields move a lot of times is that happens later. But I would be personally interested in seeing that deployed in a variety of different situations and hear, the successes or failures of conformal in these cases.
That makes a lot of sense. So I think very, I guess, hopefully, rather briefly, a final paper I wanted to talk about was you've done a fair amount of work on epidemic forecasting, as you mentioned, and COVID-19, and an interesting paper on that front that came out of the groups you worked with was a defense paper about the COVID-19 impact and trends survey, and this was sort of in response to another paper called Are We There Yet? And he described their analysis of the performance of these like large but biased surveys during the COVID-19 pandemic. And I think there's some really interesting takeaways also for the ML community here, because you talk about arguing for, this, how do we look at survey quality and how do we think about biased data sets and sort of their quality. So I'm wondering if you could maybe talk a little bit about the construction of this data set and then some of that back and forth that occurred over the quality of the survey and how that factored into actually making use of it.
I'm very happy to. So that was a maybe I'll just mention briefly that the survey was an effort that our group ran. So we have this group called the Delphi group. It's based out of Carnegie Mellon. Now I have a couple people at Berkeley with me who work in the group. I used to be at Carnegie Mellon up until a year and a half ago. And there's also members at other universities. The group works on epidemic tracking and forecasting. At the start of the pandemic, I mean, in March of 2020, I started talking to Facebook about the idea of running a survey that they would invite Facebook users to take, that would ask them a number of questions about the pandemic, everything from symptoms they were experiencing that would relate to COVID to what behaviors, risk mitigating behaviors they were taking, like, were they going out, were they attending large gatherings, to various demographic questions, to various questions about comorbidities, et cetera, et cetera. It was a long survey. It's about 35 questions typically, and this survey was kind of a collaboration between many researchers in public health, although our group was the one to host it and to kind of process the data and make it available. The questions were contributed by many researchers in public health and also people in government. So there were 11 revisions to the survey over the pandemic, where we kept adding questions that we thought were relevant and taking out other ones. And this was done in coordination with CDC and the White House, and Facebook, and various academic institutions that were kind of collaborating, or academic groups that were collaborating. And the survey was, I think it's fair to say it was the largest survey ever run in public health. I think these things are hard to measure, but I believe that's true, at least based on what people who are closer to the survey in public health world tell me. And it reached about 30 million. Well, it had 30 million respondents over the course of the pandemic. People could have taken it more than once, so that doesn't necessarily mean 30 million people. And it, I think on average, had over 50,000 respondents per day. So it was a very large survey, and it was used for tracking, for forecasting, and for policy. I think it really had maybe more implications for policy than almost anything else that we did as a group in the pandemic. So this is something that I think we're proud of as a group, the Delphi group. I asked a faculty member to kind of take over overseeing it, who works with the group. His name is Alex Reinhardt. He did an amazing job. He oversaw it for most of the pandemic. Some people pointed out, I don't remember exactly when. It was soon, maybe 6 months after vaccines came out, that the estimates of vaccine uptake based on the survey were biased upwards relative to estimates of vaccine uptake that the CDC released based on reporting. Consistently biased upwards. And so in running the survey, we already adjust for demographic differences as best we can. So we already do some kind of reweighting for the fact that the population of respondents isn't the US population. We have demographics, we can adjust for them. We ask for demographics, we can adjust for them by comparing to the census. This is a very traditional thing in survey methods. What we can adjust for is non-response bias. So you show somebody a survey, you show somebody on their Facebook front page, would you like to take a survey? Researchers at Carnegie Mellon, in collaboration with blah 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 blah, are running a survey that will help track the pandemic. It should take 35 minutes and maybe 15 minutes. 35 questions and maybe 15-20 minutes. Click here, and it would take them out of Facebook to a survey that we had implemented separately. People that take that survey are not the same distributionally as people that don't take it. People that take it are probably more conscious of public health. The idea of contributing to a survey like this would suggest that. So I think it's fair to say that it was the non-response bias that contributed to these overestimates of vaccine uptake. Right, that would make sense as well in terms of the direction of the bias. It's very hard to estimate non-response bias. I'm not a survey methodologist. We had collaborated with people who do study survey methodology as their main field. I have various half-baked ideas about how to debias and or how to kind of adjust for non-response bias. But I think if you ask somebody who works in the field, they'll tell you that non-response bias can even be question dependent. So it's not just that they take the survey or not, it's that they could take the survey and choose not to answer certain questions. And if it's question dependent and you don't understand the dependence between questions, then there's almost no way to adjust for it, right? You could try to plant questions that try to measure things that you have a ground truth for to try to estimate non-response bias. But if the probability with which people answer those questions is separate from the probability with which they answer the question about vaccine uptake, then no way of estimating the non-response bias for that one. So some people wrote a paper that noticed this, criticized the survey. I think that they were right to say that this is, these estimates were biased. I think that it's generally good in my opinion when people are scrutinous. And so in that sense, I'm happy that they wrote that paper. And they had basically found that the estimates of vaccine uptake could have been much more accurate if some very kind of detailed and more stratified sampling was done than just like shotgun sampling across the Facebook population. Our response piece was basically pointing out that this doesn't make the survey misleading for use cases that at least we believed were some of the main use cases of the survey, which is to compare things over time. Because if there's a bias that exists, but that bias is something that is slowly changing over time, then you can still compare things over time in a way that somehow is not strongly affected by the bias, right? If I'm asking for whether or not vaccine uptake improved in this population versus this population, and what I'm looking at is how much that's changed over time for each population. As long as the non-response bias didn't change, then that's somehow a relatively unbiased thing to look at. And that's how we had been treating the survey, at least in some of our internal uses and the uses that some of our collaborators were so going after was to look at the survey as an instrument for measuring changes, not as an instrument for measuring absolute quantities. So I think it is, yeah, that's my high level, is that it's very hard, I think, because of things like non-response bias to estimate, in an absolute sense, some population level quantity. But fortunately, if you're trying to estimate changes over time, or even changes over geography, if you believe that the bias is slowly drifting over time, or it's roughly similar between geographies, then you can use it to estimate changes in these ways.
One of the specific back and forths that was pretty important here, and you kind of mentioned it earlier, was the way in which this Bradley et al. Paper that addressed yours looked at this measured the data defect correlation and used it as a way to characterize the issues they saw with your data set. And you kind of take that up in this paper and discuss the limitations of data defect correlation as a way of characterizing data sets, and then argue, as you were just talking about, that we, when using data sets in general, need to use them in a way that's kind of aware of their limitations and probably be careful with the types of claims we can make given that data, given the limitations. I'm wondering if you could expand a little bit on that data defect correlation point, and then maybe how you see this broad question of characterizing, quote unquote, how good a data set is for a particular use case, and how you think about that, how you recommend people think about that.
I have to be honest, I think if I try to spend time on the data defect correlation, I would probably say something that is technically inaccurate, because I have not thought about this in a while. So I'll have to abstain from
Sure.
commenting specifically on that. I think that if I'm remembering correctly, my broad issue, and our broad issue. Alex Reinhardt and I wrote the paper together, and he did most of the kind of work on the survey, as I said, and on the paper here, was that the data defect correlation calculation, which eventually would lead you to a notion of effective sample size. So they use this to say that the original sample size was 30 million. The effective sample size was only very small. Somehow it was like you could somehow work out what an effective sample size was through this data defect correlation. So it would have been, it would have given you some error proportional to an unbiased sample of only, a couple thousand or whatever the number would have been that they found. That to me is, I think that the issue that we had at a high level is that it's confusing bias for variance. So when you have an unbiased sample, the variance is what kind of, or the sample size drives the variance, right? And so that's how they had worked out what so when you have an unbiased sample, the only contributor to the error is the variance, and the variance is controlled by the sample size. When you have a biased sample, like your error now has, bias and variance components. Yes, you could ask, how large of an unbiased sample do I need in order for the variance to match the error that I see? But that's I think that's a kind of a weird conclusion, because it confuses bias for variance. And if bias isn't changing, then somehow we can, like over time, then we can somehow account for that by taking differences over time. And that doesn't, and then we don't have a survey that's, of a tiny effective sample size. Then we have a survey that's of a very large effective sample size if we've done this properly. So that was, I think, that at least the high level issue with data defect correlation. Measuring, what you asked is a good question. I find it's very tricky, in my opinion, to measure data quality in epidemic tracking and forecasting. And there's a larger set of issues that I thought about that relate to this that I'll mention, which is, let's suppose you're a public health agency. You work in the county public health department. You have limited resources, like many counties do, or maybe even many states do. We can say you work in a state department as well. And somebody comes along and says to you, I have this great data source, and it's going to change the way that you track COVID, or it's going to change the way that you track influenza or RSV or something. It's a leading indicator, in fact, of those things, which is a term that gets used a lot. It's a leading indicator of COVID. You should use it, and maybe even you should buy it. I'm a company. I'll sell it to you. I'll sell you access to it. That's very tricky. I think whether you should engage is a very tricky question scientifically. Even if it was free, it's a resource cost to try to kind of keep tabs on one more data stream. And it turns out that there are many ways to quantify what it means to be useful, and I kind of think that all of them have objections. You can find objections to all of them. And correlation is one. You could ask, how well does the thing correlate with the thing you're trying to measure? You can ask, how well does lags of the thing that somebody claims is a leading correlation correlate with the thing you're trying to measure. So let's suppose I tell you that I have a smart thermometer that'll predict flu. And it's a 2-week leading indicator. It's a week leading indicator of flu hospitalizations. Then you might think that correlating the measurements from these smart thermometers with hospitalizations a week later would result in large correlations. That's like one correlation-based measure. I could also say, well, why don't I add it to a forecasting model of flu? I have a forecasting model of flu. I'll add to that forecasting model this new feature, which is like the smart thermometer measurements. Does it improve forecasting? I could do other things. There are different kind of categories. There's something called Granger causality coming out of economics that is another take on this. I think all of them, in my opinion, have some limitations and some flaws. And there's a rich literature on this in economics, at least. And it's I think it's too bad that we don't have a go-to method to recommend to practitioners. So at some point, if I have the energy for it and can make time for it, I was planning on writing a kind of a survey of here are the methods available for assessing leadingness or assessing data quality. Here's what they are. Here's their flaws. Here's the pros and cons. Just because I think then at least it lays it out there. At least this is maybe aimed for people in Epi more so than other fields. But it's a very tricky question. Is the kind of my summary is that we have methods to assess that. They have varying complexities, but I think that none of them are foolproof, and you can find ways to distrust any of them.
I think that's a really important note. I think this might be probably a good place for us to close things. And I do want to say thank you for being so generous with your time. It was really fascinating learning about your work, and I appreciate everything you're doing.
Oh, thank you. Thank you for inviting me, and I thank you for what you're doing with this podcast. I hope that some fraction of what I said made sense. And if not, then you can have me back at some point, and I can either answer things differently or answer different questions.
Thank you for listening. Thank you to my guest, Ryan Tibshirani. You can help out if you enjoyed this by leaving a rating, by sharing this with people. And for comments, feedback, guest suggestions, you can always reach me at editor@thegradient.pub.